Welcome to the NMR physics class. I'm Graham Mason, teaching this course together with Robin de Graaf and Henk de Feiter. Today's lecture will cover four main topics. The pulsar choir experiment, which you will see repeated at various times through this course. It's the simplest of all NMR experiments. We'll cover a concept called the rotating frame and discuss Bloch equations, and then T2 star relaxation and a spin echo experiment. So we start with this Bloch equation. As you've seen in the previous lectures, in the presence of a strong magnetic field, which is called in NMR jargon, it's called B0, there's one of the consequences in a set of spins, a sample that has nuclei with spin, is that we develop a net magnetization. It's possible in the presence of a radio frequency. We adjust the right frequency, then called a Larmor frequency. If we apply an oscillating magnetic field called B1 at that frequency, we can cause this net magnetization to rotate. If we rotate it into the XY plane, then we have a situation in which there is net magnetization precessing around the axis of the magnet, around B0, and that's precessing in the presence of a detector, a conductor. When you have a magnetic field, even if it's small, like the one generated from the coherence of all these spins in the sample, when you have a net magnetization precessing near a conductor, that magnetic field, it's a changing magnetic field that oscillates over time as it spins around, that generates an electric current in the conductor, and that's what we detect. So the pulsar choir experiment consists of taking the net magnetization and rotating it into the XY plane to some extent so that we can detect a signal. I'd like to point out here that for those of you who were doing clinical studies, magnets for humans are almost always horizontal bore. So B0, even though the picture points it up, B0 is actually horizontal for most human applications. And accordingly, this Z-axis, which is pointed up, in physical reality, this whole graph would be turned on its side. So the XY plane is actually tipped. But by convention, you will always see the graphs this orientation. So get used to this. Now, as the spins return to their initial orientation along the Z-axis, they are precessing here and they emit energy. As long as they stay coherent, we can get a signal. Now, in a general case, how far we can tip this, it's usually drawn as a 90-degree tip. We can tip this to many different angles. We can tip it around the y-axis, we can tip it around the x-axis, we can tip it somewhere in between, and we can make it rotate slowly and then quickly and slow it down again. But all that matters when we go to detect our signal is what is in the XY plane. The next topic is the rotating frame. And this is a matter of perspective. It greatly helps with the ease of understanding how NMR experiments will work. So we have a big dog, and he's watching a puppy who's watching a bone. The puppy is going around on an old-fashioned record player. He's precessing. He's like rotating, like the nuclei are precessing. The nuclei are precessing for a 3T magnet around 123 megahertz, 123 million times a second. So if this little dog were spinning around at 123 million times a second, to the big dog, it would just look like a blur. It would be very hard for the dog to calculate exactly where the dog and the bone are at any given moment. Now, if we put ourselves in the perspective of the small dog, if we could get on this record player with the small dog, it would look to us like the dog was holding still, the bone was right in front of us. Nothing would be, it'd be very easy to bend over and pick up that bone. Um, so that is the rotating frame. The big dog is in what we call the laboratory frame. The small dog is in the rotating frame. So the rotating frame is putting ourselves in the perspective of something moving at the Larmor frequency. And this avoids a lot of complication in calculations. Of we can watch magnetization tip and return to Z, and we can watch it dephase without having to concern ourselves with a rotation that's hundreds of millions of times every second. Here's a video of a cat. If the cat could read, it would be easy. It would look like the letters were holding still for the cat. For us, we have to catch the perspective of the letters on the way around. So we've described conceptually how to consider a vector being rotated in presence of this B1, this oscillating magnetic field. And we've talked about the rotating frame. But a formal way to look at this is through what's called the Bloch equations. The Bloch equations are a set of expressions that define all the possible motions of the net magnetization. And in the general form, it has many terms, and we'll break those down here so they become a little easier to understand. In the first case, well, because we do most of our analyses in the rotating frame, we don't have to worry about the precession. This gamma B0, that's the Larmor frequency that has been brought up several times in the course so far, which at 4T for protons, this is 170 million times a second. For 3T, it's about 123 million times per second. We can ignore these terms if we are going to put ourselves into the rotating frame. When we are considering what happens while we have an excitation, what's drawn up here, we have the magnetization is in the process of rotating from Z into the XY plane. So while there's a rotation going on under the influence of B1, we can ignore all the other terms because B1 applications generally are on the order of microseconds or a few milliseconds at most. These T2 and T1 processes I'll talk about later, we're talking about tens of milliseconds usually, or seconds. So this B1 application occurs practically in an instant compared to these other things. So when we're talking about B1, which is the jargon for the oscillating magnetic field, we can ignore most of these terms and focus on what's yellow here. Then when we talk about T1 and T2 relaxation, because those are so slow, we can usually ignore everything else. So when we are actually using these Bloch equations, we're really only using a few terms at any given time. So here, while we are calculating the B1 effects, if you want to figure out over time as you apply B1, what's happening to the net magnetization, we can eliminate all the other terms and we're left just with this. These are differential equations. So if we examine the case of a Bloch pulse, that's a pulse that looks like a Bloch because it turns on, it's left on at a constant level for a short period of time, microseconds or maybe a millisecond at most, and then it's turned off. The pulse width is it's called T sub P here, and here's the B1, that is the amplitude. So if we rotate this pulse, we're actually able to, we won't talk about it now, but we are able to determine which axis we rotate, about which axis we rotate. It could be about the X, Y, or something in between, but we rotate about something in the XY plane. And the vector moves to a right angle position with that. So if we decide we're going to rotate about the x-axis, Um, there, and we're starting with no magnetization along X. Um, we're taking Z magnetization and rotating it through an angle theta. And that angle is equal to gamma B1. That's how quickly, how many degrees per second this thing rotates, times the pulse length. Um, and so we gain signal in X, and we lose signal in Z because the signal is coming out of Z and going into X. That's true for a small angle. Go down to 90 degrees. If you go past 90 degrees, you begin to redevelop magnetization in Z, and you start to lose it along the XY plane. So we were taking Z magnetization, converting it to Y magnetization, and then moving it to Z. So note that just because when you apply more B1, it doesn't necessarily get you more signal. The optimum signal you can get for one experiment is to rotate it 90 degrees. If you apply more B1 than that, you will rotate out of the XY plane and get less signal. If you rotate yet more, you can rotate the magnetization all the way here to the negative Y-axis and gain signal again, and so on. You can actually spin the signal around and around. There are some experiments where we do that, but it's unusual. Here's an illustration of what I was just talking about. You can rotate. If you rotate into the XY plane, you get the full net Z magnetization vector as your signal. If you rotate a little bit, it's whatever the projection onto the XY plane is. If you rotate a lot, more close to 90, you get more. If you rotate, say, 170 degrees, you get just a little bit again. Because what matters for the amount of signal we get is how much is in the XY plane. And as we will discuss later, there are occasions when it's good to rotate just a little bit. Some of the imaging experiments is that those of you who are going to do, say, functional imaging, there are some cases where you don't want a 90-degree pulse. You actually want a smaller tip. There are some cases where we want to develop what's called T1 contrast, for example, where we may tip all the way to the minus Z axis. We will talk about those later. Now suppose we're dealing with T1 relaxation. There's the time it takes after we've tipped the magnetization to the XY plane, there's the time that it takes for it to reform along the axis of the magnet, the Z axis. This is also true when you put someone in the magnet for the very first time. It may take a few seconds for the net magnetization to develop in the tissue. Normally, by the time you set up the MR study, there's been plenty of time to reach full magnetization. But if we do a pulse, we need to redevelop Z magnetization before we can acquire another signal. So we have to allow enough time for that to happen, and that's governed by T1 relaxation. So this yellow component is all we have to worry about with that. Here is it's a general expression when we're talking about T1 relaxation. This is all we're usually concerned with, not all the other terms. And the general solution is this. So the M0 is the net magnetization. This is NMR terminology. The M0 that is typically used as the net magnetization that you'd allow to develop after some time in the magnetic field. MZ parentheses 0, that means whenever you start measuring from 0 to some time t, where was the magnetization when you began tracking its fate? In this case, if we tip into the XY plane, MZ, that's Z magnetization, is 0. If we tip all the way into the XY plane, there is nothing in the Z axis. So this would be Z, 0. In this picture, it's about a 60-degree tip, so there's a little bit of Z magnetization that we plug in as this initial value. If we want to do a general case, we take this expression and plug in whatever this initial value is. Now, keep in mind, and it takes, if you were to plug in, say, 0, which corresponds to a 90-degree pulse, and you may want to try this in Excel, to plug in this equation and track for a whole series of values of small t versus t1, track how long it takes to recover full MZ magnetization, the full M0. T1 for CSF may be 3 seconds. T1 for white matter could be around 700 milliseconds. So you can, what you'll find is it can take 1, 2, 3, 4, 5 seconds or more to develop M0 again. If we don't wait long enough, and not all of the M0 recovers, if it's fully formed, then we do another tip. It's that diminished M0 that's going to give us the signal. So we're going to observe a smaller signal. That's called T1 saturation. It sounds like a bad thing, but there are times when we actually make use of it. Now, this other thing, it's called relaxation. This is T1 relaxation. Now we're going to talk about T2 relaxation. Now, again, because T2 occurs on a time scale that's much longer than the B1 actions, typically, and it's substantially shorter than T1 normally. We usually only consider T2 actions by themselves. So now we're done again to a simple equation. And if you were to solve this differential equation, you would find exponential terms. So this T2, say T2 loss shrinks vector is what this says. When we first tip into the XY plane, there is coherent XY magnetization that can interact with the conductor, that is our detector. Over time, this T2 relaxation zeroes this out. So there is no net XY magnetization, and we can't see anything after that. This occurs because of interactions of what we're observing, the spins that we're observing with other spins in the system. So here's a case of a long T2. That means it takes a long time for these interactions to decay the signal. Here we go, we tip into the XY plane, and after some time, maybe 20, 30 milliseconds, we see the magnetization. Different spins are now spreading out because they are giving up their energy to different, to other spins in the sample. And that causes them to move a little bit out of phase with where they were before. So this is sitting at the rotating frame, and this one's a little off the rotating frame, and this is farther off, and that's in the other direction, they're off. And eventually they spread out completely so that each one of these spins is in the XY plane oriented. It's generating a tiny magnetic field that can generate a signal in the wire. The problem is that for every one that's over here, there's also one opposite to it. Those are generating opposite phase signals in the currents in the wire, and they cancel each other, so we see nothing. Now, if something has a very short T2, maybe this is just a few milliseconds, and it's already spread out much more than what we saw up there. We reach this full T2 relaxation, this fully decayed signal in a shorter time than with a long T2. The equation for it is that how much magnetization do we have if you take the X and the Y, put them together, what's the total XY magnetization? Well, we started out with M0, and this little t is how long after it reached the XY plane. As the equation shows, it's an exponential decay. The signal dies away, and you could plug this into Excel too and just try some different numbers, and you'll see that when T2 is short, this decays for any given value of little t, for a short T2, you will get less signal than you have for a long T2. Now there's another effect. We'll talk about T2 star relaxation and a spin echo experiment, which is actually related to, conceptually, to the T2 star relaxation. So the T2, as I just described, is the time constant for coherence loss that's due to interactions with nearby spins. T2 star This is something that it looks like T2 in its dephasing capabilities, but it's not the same thing. This is lost due to the T2 and also to magnetic field inhomogeneities. That inhomogeneities term is called T2 prime. When we put them together, the T2 that's inherent to just the way a molecule is in its environment with some degree of magnetic field inhomogeneity present, we end up with what's called T2 star. And again, I've described this as a signal loss, which sounds like a bad thing. But like many things in NMR, what in some contexts degrades your signal, in other contexts can be something you can exploit. It could give you extra information about your sample. One consequence, if you go through and plug in some different values for these numbers, you'll find that T2 star can never be greater than T2. T2 is the best you'll ever get as far as this phase, this relaxation rate. And there's really nothing we can do about T2. That's just something inherent to the molecule in its environment. There are often things we can do about the T2 prime part. But if you're looking for the best T2, the longest T2 star you can ever get, this is it. So here we have T2 alone. T2, maybe this is a long T2. It takes it, but some dephasing will inevitably occur. Now we take some inhomogeneity, and instead of we still have this stuff from the top going on, but now imagine you have an image pixel, and this image pixel is somewhere near a person's ear canal. There's an interface between the air that's in the ear canal and the bone and the brain. Whenever you have an interface of tissues that have different magnetic susceptibility, there's another jargon word, you'll get a distortion in the magnetic field. So you may, if you've stood in a swimming pool and looked at your feet, you may notice that your feet don't look like they're where you know they are. That's an index of refraction that causes that. When light passes through the surface of the water and the air, they have different indices of refraction, so the light bends. And now here we have a magnetic field, and when the magnetic field lines go through two materials with different magnetic susceptibilities, the magnetic field bends. So if you have your image pixel, right, tiny as it is, near an interface like that, of brain and air, one side of the pixel will see a slightly higher magnetic field, more B0 than the other side. The other side will see less B0. Remember that equation that keeps coming up. The frequency equals gamma times B0. When you have more B0 in one place and less B0 in another place, they will have different. One will have a higher Larmor frequency than the other. And if you put yourself in the rotating frame of, say, the middle of that pixel, if you look to one side of this little tiny pixel you're sitting in, you're going to see the magnetization over there at the edge of the pixel rotating away from you. And you'll look to the other side and you'll see it rotating away from you in the other direction. So these will, based on where the spins are sitting in your pixel, they're going to be rotating away from the middle but in one direction or the other, and they will dephase. And you may have the perspective that you can look to one side of the pixel and see spins moving, or to the other side and see spins moving. But the acquisition for your MRI is just going to see a pixel. It's going to look at the average behavior of the magnetization through that little tiny pixel. And once it's dephased, once you have vectors that have moved away on one side versus another side, then the signal in that pixel will be averaged to 0. So effectively, when you have a short T2 star, the image pixel intensity drops, and it drops quickly. And here is a gradient echo image. And see along here, this looks like a mouse chewed on the bottom of this person's brain. And that was not the diagnosis for this subject. See over here, same thing. There's distortions, but also big major signal loss down here at the base. Um, and these are due to macroscopic inhomogeneities, like I just described. We've got their sinuses, bone, the mouth, if we were looking farther up in the front of the brain. These things, the ear canals, they can all cause signal dropout like this. Now, something else that's interesting in these pictures is notice here in this thalami. There are microscopic inhomogeneities. So this is a T2 star. Instead of it being a big disturbance across space, like caused by the ear canals, these are microscopic disturbances. And as we age, we tend to accumulate iron and minerals. I've seen this in the white matter, the cerebellum, and here you go. Here's in deep brain structures. So that when you deposit a little bit of iron there, that causes a very local distortion of the magnetic field. But it may be local and it may be small, but it gives you this effect of a signal dropout. This is something actually you can exploit. We'll talk about it later. But for fMRI, you rely on this for most approaches that use fMRI. There's the Bold effect, blood oxygen level dependence. Oxygenated hemoglobin distorts the magnetic field. As you might imagine, hemoglobin has iron in it, but it distorts it very slightly. Deoxygenated hemoglobin also has iron in it, of course, but it distorts it much more severely than the oxygenated version. So we sit here and you sit and watching this video. Hopefully you're relaxed while you watch it, and you have some ambient level of deoxygenated hemoglobin at all the places in your brain, and they're causing some ambient level of T2 loss around your blood vessels and your capillaries. If you turn this lecture off and start playing some very stimulating video game, lots of flashing pictures, and we were to do take an image of your visual cortex, it would be more highly stimulated than it is right now. Now you might think that, oh, it's stimulated, the nerves are doing more work, they're pulling oxygen out of the blood, the deoxygenated hemoglobin will rise, but that's not what happens. What happens is that to maintain the necessary oxygen level in the brain for those nerve cells to have their elevated function, the oxygen levels in the blood, the oxygenated hemoglobin levels in the blood actually rise. That maintains a concentration gradient of oxygen to flow into the brain, and you decrease the amount of deoxygenated hemoglobin in the regions where there's stimulation. That means the T2 star effects go away a bit, and you get a very slight signal increase in those regions. T2 star becomes a little longer. It gets a little closer to the natural T2 of the tissue surrounding the blood vessel. And when I say slight, I'm talking 0.5% or 2%, and maybe a few percent. It's very slight. It's enough that if you just look at an image when someone's in a stimulated state, you are very unlikely to see it. But if you do a pixel by pixel comparison across a series of images, then it can become apparent if the stimulation is strong enough. So that's an example of why T2 star can be a beneficial thing. So here we are. I have a movie of losing T2, losing magnetization due to T2. We start with Z magnetization. With B1, we rotate it into the XY plane and then open the receiver. And while the receiver is open, look at that, it spreads out. The signal goes away. If we watch that again, here we go. We tip into the XY plane, and then when the receiver opens, the magnetization spreads out and our signal decays. If we could recover some of that lost signal, it could be very helpful. So here is something called the spin echo sequence. I'll show you a movie of this in a moment. We start with Z magnetization, tip it into the XY plane. So this is just a pulse acquire start to it. And we don't open the receiver, but we wait a bit. Something called an echo time. We're waiting for half of TE, half of the echo time. And what I've drawn here in red, these now this is just isn't T2. This is T2 star. So we're ignoring the T2 dephasing. We take our original vector, and now the one side of the pixel, image pixel, is rotating counterclockwise because it's got a little bit less B0 in it than the other side. So that's the red vectors. Here we have the yellow vectors. They have a slightly higher B0, and therefore a slightly higher Larmor frequency. So they're not exactly with us in the rotating frame, and they'll rotate clockwise. Notice that if we just opened the receiver during this, we would lose phase coherence, and this would be to have a T2 star decay. But instead, we apply what's called a refocusing pulse. This is where refocusing it has to be a 180-degree pulse. And now we take anything that was on this side of us. Here we're sitting at the orange vector in the rotating frame. Anything that was sitting on this side flips over to the other, and vice versa. Anything that was over here now moves over to here. So notice that we used to have red vectors on the right and yellow vectors on the left. Now we have the yellow vectors are over here and the red vectors are over here. Now we moved the orientation of the vectors, but we haven't actually moved their physical location. So whatever was sitting closer to the ear canal is still sitting closer to the ear canal. And what's farther is still farther away. So these red vectors are still going counterclockwise because they have a lower Larmor frequency. And the yellow vectors are still going clockwise, even though we changed the orientation of their vector. If we match the length of time, the echo time, for here versus here, and then we open the receiver, we will pick this up right at where these refocus. Whatever phase coherence is lost due to the inhomogeneities will refocus for us with this scheme. And we start out with the full intensity as if we had only T2 decay. The time delay here is typically, it depends what you're doing. It could be a few milliseconds, it could be 20 milliseconds or 50 milliseconds. It depends what your purpose is. But by doing this, you will reverse the phase coherences due to the inhomogeneities. Here's a movie of that same thing. We'll start out with Z magnetization. We tip into the XY plane. We get dephasing. But now there's the refocusing pulse. And by waiting the same length of time, if they moved 45 or 60 degrees during the first echo delay, they're going to come back 45 or 60 degrees. That's why they refocus. So we'll see that refocus a second time. Now, if we go to a worse scenario, the question you may wonder, will it still work? And yes, but here's it drawn out. We get tip into the XY plane, we get dephasing, and see it's farther out. Then comes the refocusing pulse, and things that precessed 80 degrees will come back if you allow the same length of time. Now, there are, aside from fMRI, there's some reasons to do spin echo imaging. Here's a picture, an axial view. So you're pretty near the sinuses. If you were to do what's called a gradient echo image, that's like a pulse acquire, where you do not get T2 star compensation. There's often a hole up here. If you do a T2 star compensated, a spin echo image, we recover this dropout. Now there's something else that's happening in this picture. Notice that the CSF, cerebral spinal fluid located in the ventricles and the sulci, is very bright. Now that's because there is T2 loss. That may seem a little backwards, but the T2 of the CSF can be hundreds of milliseconds in length. The T2 of the white matter may be 60 milliseconds in length. So during our spin echo sequence, we do recover T2 star, but we still lose with T2. So that means during a spin echo sequence, things with short T2, like white matter, will lose more signal than things with long T2s, like CSF. Gray matter is in between, so the gray matter is a little bit lighter than the white matter. So a spin echo image will emphasize features with long T2, like CSF. So suppose you had a patient with a potential diagnosis of multiple sclerosis, and on one sort of image you saw what looked like a hole in the white matter. If you were to do a spin echo image, you might see a bright spot in that white matter. And that would mean, well, that's probably not a brain bleed, which would have iron in it. That is probably filled with fluid from CSF. It's a lesion in this patient. So the T2 can be used to, not doing T2 star can be used to give you some fMRI contrast. T2 can be used to give you contrast that tells you something about the brain tissue or tissue in other organs. For those of you who will go on to do NMR spectroscopy also, T2 and T2 star have a consequence, a pretty strong consequence. This is a simulated spectrum with two peaks. They're separated by about 20 hertz. Here is a small peak and a large peak. And the simulation has been done here assuming a T2 of 50 milliseconds. Now, suppose T2 were only 20 milliseconds. We're going to do a spin echo acquisition, so we begin with full magnetization. But once we open the receiver, we don't get any more refocusing, and the signal dies away. We start the area of the peak is the same for the shorter T2 here and the 50 millisecond T2. But note that the peak is shorter in height, and it's broader. These peaks are not really separated anymore. They're beginning to blur together. And you could, with peak fitting, you could make an estimate of these two peaks pretty reasonably. Now let's go to, but they're not so clear as they were with the long T2. If we have a short T2, very short, say T2, maybe T2 star, because of where we are in the brain, near the sinuses or the subgenual prefrontal cortex, maybe the T2 star has dropped dramatically, and it's only 10 milliseconds in our MR volume. At this point, even if we do a spin echo measurement and we start out with our full amplitude of magnetization, once we open the receiver, we do get the decay. And the peak areas, the big peak and the little peak, combined, they remain the same, but they are blurred together to the extent where you can see that there are two peaks, but it would not be reliable to measure them separately. So for NMR spectroscopy, it is very important to diminish the star component, the magnetic inhomogeneity component, as much as possible in our experiments. A rule of thumb is that generally the width of the signal is 1 over pi times T2 star. So 1 over pi times 10 is going to be broader than 1 over pi times 50. So to summarize for today, magnetization can be rotated in space under the influence of applied radio frequency. And the standard term for that is B1. This is opposed to the standard term for the large magnet, where the term is B0. So people often ask me, oh, is there a B2? And actually, there is a B2. We will talk about that in a later course. It's the same as B1, but used for a different purpose. But yeah, so B1 is what you normally will encounter in most things that you do with MRI and MRS. This rotation is followed by an observation of XY magnetization, and that's all you do is rotate and then see what's in the XY plane. That's called a pulse acquire experiment. That's the simplest NMR experiment, and it's the basis for a lot of spectroscopy and MRI sequences. So then we talked a little bit about the rotating frame, and the rotating frame is where almost everything that you will read about is presented. They usually won't say it because it's so common. Rotating frame is a perspective of being of you rotating together with the the net magnetization in the XY plane. You precess at the Larmor frequency. So it actually, from the perspective of someone in the rotating frame, it looks like there is no precession. One example is the playground toy, where it's a metal platform. Sometimes it's called a merry-go-round. The child sits on there and someone starts it spinning. And standing in the laboratory frame, which was where most of the parents are, watching from the side, you see your child spinning around and maybe holding a toy. If the child sets the toy down on the merry-go-round, the toy looks stationary to the child because the child is in the rotating frame. The parent sees both things rotating. We are in the laboratory frame. That's how a playground can become a laboratory. So it just makes the rotating frame makes things look much simpler, easier to understand for when we evaluate NMR experiments. And magnetization can be rotated in space under the influence of applied radio frequency, but it also decays as phase is lost due to T2 star and T2. We can describe, and there's also T1 relaxation, which isn't mentioned here in the summary, but that's returning from the XY plane, or from wherever we've put the magnetization, to its resting state, so to it returning to its Z orientation. All of those things, the B1 rotations, the T1 relaxation, and the T2 and T2 star relaxations, those are all governed by the Bloch equations. Now, we can actually, the T2 star will wipe out some signal from what we can detect. And it's very helpful if we can recover that component. And we often do this with a spin echo experiment. So when the transverse magnetization is rotated by, we let the transverse magnetization begin to decay, then we rotate it again by 180 degrees. It's called a refocusing pulse because it will allow us to refocus the defocused magnetization. As long as we have equal delays before and after that refocusing pulse. That's called a spin echo experiment. The sequence is the basis for a lot of MRS and MRI experiments. It's only slightly more complex than the pulse acquire study. And this concludes the second lecture in the NMR experiment, in the NMR course.